My name is Paul Rako. This is the Atmel Edge, the show that makes you well-rounded and well-grounded. The show's for engineers, makers, hobbyists, technicians, anyone who wants to learn about electronic system level design and some firmware, some software, and even a little mechanical engineering thrown in. Today's show is Schematics 103. Still on grounds, this is the well-grounded part of the show. Schematics 101, we talked about the difference between earth ground, chassis common, power supply return. Schematics 102, we introduced shielding and how that caused a huge problem at a semiconductor machinery manufacturer. Today we're going back to my old auto business experience in Detroit, and we're going to tell you about how misunderstanding shields and grounds and chassis commons caused a huge problem for an automaker in Detroit when I worked there. So let's get started. Okay, Schematics 103, rid of my favorite Staples graph paper. Everybody gives me grief. I've got a little bonus thing we'll talk about after the main segment here. I was at a major auto manufacturer back in Detroit, design engineer, electrical department, huge volume, pickup truck. And what had happened is Canadian regulations back in the 80s had gotten more strict for radio emissions, for radio interference coming from vehicles. Up in Canada, they love their radios. They need to communicate. It's a lot of snow and ice. So they were stricter than the American standards. To my knowledge, automobiles don't have to pass the FCC regulations for radiated emissions like a computer or an electronic device. One of the problems that made it worse is that the inner fenders were plastic in this new model of vehicle, a 1980 vehicle. And that plastic allowed the radio waves to emit out from the tires and that and cause interference. And there are things like switching spikes in the diodes in the alternator as they commutate back and forth. That creates noise. The ignition, of course, is the big noisemaker, those 40, 50,000 volt high energy ignitions. So let's make a blue car here. We'll see how good my memory is. So here's the automobile, and we'll put a dashboard here, windshield. And let's see if I can remember all this auto business jargon we used to have. The area along the edge of the fender that the hood closed over is called a racetrack, if I remember right. The front, the radiator support, was called the horse's collar because it has a hole in it for the radiator air to get through, so it looked like a collar you put on a horse. The motor, we'll do a V8 because I'm old school. Here's the motor. And the fan there. So black, we'll use black for the tires. That'd be appropriate. So here's the tire. Here's the tire. Put some tread on the tire. Great. And those inner fenders, well, we'll use red because that was the problem. The inner fenders were plastic. It was letting a lot of noise out. So we'll draw those here in red. And of course, they're right by the ignition wires. The spark plugs are right down there. So it was just letting a lot of noise radiate out through the vehicle and causing it to fail standards. Our first concept was to reduce the amount of noise emitted from the vehicle, while the hood was we found out, letting a lot of radiation pass. So we decided, well, let's take the hood and ground it. And of course, that's a joke. Howard Evans would give me some grief about that. How do you ground something in a car that isn't attached to ground? And that just proves my point, how sloppy engineers get about terminology. Let's say it this way. Let's attach the hood to the chassis common, and that way prevent the ignition noise radiation from coming out through the hood. And you might say, well, the hood's metal. How does radiation? This is the problem. There's galvanic connection where you could take an ohm meter and measure 0 ohms because the hinges and that connect the hood to the body of the car. But that's not at RF, at ultra high frequencies. There's a lot of antennas that are pounded in the ground on one side and then they radiate out the top of the antenna. And that's the problem you have in a car hood. So our first instinct was to take an 18 gauge wire. Back in those days, it was a penny a foot and a penny a termination. And take a nice copper, low impedance 18 gauge wire and connect it to a bolt on the hood and a bolt on the chassis of the car. If I remember right, let's do it in green here. So here's the hood. We'll draw the hood. coming over. Actually, it goes all the way out to the front, doesn't it? And so the hinge assembly back here, we took an 18 gauge wire and we connected it like that. Hardly any improvement. Unfortunately, we had guys in the department like Ed Winstead, who'd been in the Army Radio Corps. And there's ham radio guys or other people that are great to talk to about these kind of problems. He said, well, having that little corner grounded is really not significant in the RF field and in the gigahertz range. It's just an antenna. It accepts the noise coming in from the engine and just rebroadcasts it out into space, and we failed Canadian emissions for automobiles. So our first instinct was then, okay, well, we've really got to get a good ground. Let's take a little strip, a little spring strip with prongs on it and dig through the paint. Well, like any big company, you know, the automobile companies have all these departments, and the body people went nuts because they have to pass salt spray. They have to ride the car through salt water and not rust. I said, you're not cutting through the paint with your little RF prongs no matter what you do. So the 18 gauge wire didn't work. Couldn't sell having things scrape when you close the hood, scrape through the paint. So then we looked at braided wire, and RF travels on the outside. It's called a skin effect. So by using a braided cable, and you'll see it on many times on the battery going from the engine to the frame of the car, a braided cable has lots of surface area because there's all these little braids, and that can help make the RF, it lowers the impedance at radio frequencies, which is what we needed to do. The other solution that we proposed to the body guys is to ground the hood all around the edges. You see for industrial applications, all these companies that sell strips that you metallically connect the panel all the way around the edge intimately with the chassis of the machine, and that prevents radiation. Well, that was totally impractical in a car. The hood just floats. So what we settled on was first going to a braided cable in the corner, and that helped a little, but not nearly as much as you'd think, because the whole hood was still kind of floating, well connected even at RF, but still a big antenna. And then we went back to the things that are just basic. When you have noise problems, go to the source and kill it at the source. It causes a lot of benefits all through the program, where if you kill it at the source, well, then it doesn't get into the power supplies and go through all that wiring and just radiate somewhere else you can't control. So we went to the alternators, increased the size of the capacitors that damp out those switching spikes and the diodes. We went to the ignition. We, of course, were terrified of having to go to braids around the ignition the way an airplane does, propeller prop-driven airplane with a conventional engine, because of the cost. That would just be astronomical. But with resistance wire to put some damping in the system and lower some of the peaks, we managed to get through radiation, and I'm sure that's still a problem to this day. So there's a little tip for you of when grounding isn't grounding, when connecting a wire between two metal panels really doesn't do what you think at those high frequencies where you've got interference problems. And this FCC, CE radiation, and then CE immunity is even harder. These are all problems that come up at the end of the design cycle where you least can afford it, where you're trying to ship product. So this is a good trick to think in terms of RF. Talk to ham radio folks. They'll explain a lot to you about shielding and things like that. So keep it in mind, Schematics 103, and hope to see you next time. All right, so we have a little bonus feature. We've got our car here. I found as I'm archiving all of my design work that I've done when I was a consultant. I came across this thing when I was at Hewlett-Packard. It's a ground loop study, and this gets back into the what's a ground, what's a chassis common. What we were making is test equipment for cars. So you hook it up to the car, the J1962 connector, I think it's called, and that you can read in and see what the error codes in the car. And this is back decades ago. And you can see I had to do this drawing just to keep track of the kind of problems. So you can see that the car is right here. There's the front of the car. Here's the tire of the car. It's on dyno rollers here and here. There's the motor. I did a transverse motor. And you can see the kind of problems. If the car is in a garage being evaluated, it could be connected to a gas analyzer, the pollution, smog control stuff. So that whole system has one ground, and that was connected to this module, this CIM module that we were designing. There's a host computer, and it has its ground with a dock. There's the engine analyzer module, which is another gizmo we were making. It's connected to the car, but then it goes through the host and picks up earth ground there. And of course, like I've pointed out, there's only one real earth ground, and that's this copper rod. That earth ground is the third prong on your wall socket. That's a real earth ground. Everything else is chassis common or power supply return or something like that. So I had to do this drawing just so we could understand all the ways you can seek ground and all the kind of ground loop problems we could have. Ask an audio expert or a musician about ground loop problems. So there's another little bonus thing about just thinking about grounds. It's not a trivial thing. That little symbol on your schematic doesn't make it true. You have to think where the currents are flowing, especially if you have large currents. You know, battery starting currents, things like that, output section for a motor or speakers. Those currents will interfere with the more delicate currents. So you've got to think about where your returns are and how they get isolated and how you can keep them apart from influence each other. So there you go. Atmel Edge. This is Schematics 103, well-rounded and well-grounded. Catch you next time.